Okay, this is the last video in Chapter 9. This is the part 10 video on glycosides and glycosidic linkages. And what we're going to do here is go over how glycosides are formed from our pyranoses. So remember that our sugars can cyclize into this pyranose form, as you can see with glucose. Here's the open chain form. Here's the closed chain form. And the closed chain form can form this glycoside. So you notice that the OH here is being converted to an OCH3. And also the stereochemistry at this position is changing. So here the OH is up, and after this reaction, you're getting both the OCH3 down and up. So this glycoside formation, you notice this double arrow means that it's reversible. So once you have the glycoside, you can just add water and acid to go back to the pyranose form. So methanol and acid will give you the glycoside, and water and acid are going to give you the pyranoses back. So we're going to look at the mechanism, but just to briefly kind of walk you through the mechanism and try to see if you can draw it out on your own before we look at it. But what's going to happen here is we are going to protonate first because we are in acidic conditions. So we're going to protonate our OH here. This is going to be a good leaving group, so it will fall off as water. Once it falls off as water, you'll get a positive charge here, right? A carbocation intermediate. This is going to be resonance stabilized by the oxygen over here. That's why we can get that to form nicely. And then instead of the water coming in, we're going to have our methanol come in, and the methanol will come in and then it will get deprotonated. So there'll be a proton transfer as the last step. So give that a try, see if you can walk through that on your own. And on the next slide here, so if you pause the video and kind of give it a try, and then on the next slide, we're going to walk through the mechanism on the slide. So here's the mechanism for the formation of the glycosides. Again, as I mentioned, the first thing that's going to happen is a proton transfer. The alcohol is going to get protonated by acid. And remember to notice that what we're doing is we're protonating it with an alcohol that's already been protonated by the HCl. So if you go back to the previous slide, the alcohol is going to get protonated by the HCl, and that is going to act as your proton source to protonate the OH that's attached to the glucose here. So once that becomes protonated, we have a good leaving group. Remember, hydroxide can't just fall off because that would be a bad leaving group. So now it can fall off. We're getting a carbocation here that is resonance stabilized. So you'll see the resonance form over here. That's why it's a very stable carbocation. And then the alcohol can come in. And the alcohol can approach from either side. We have a carbocation intermediate. So just like an SN1 reaction, we're going to get approach either from the top or the bottom face. So we're going to get a mixture of stereochemistry at this position because it is an SN1 type reaction. So once this coordination has occurred, then we're going to see another proton transfer to deprotonate the alcohol. And this is kind of showing you, okay, what happens if it comes in from the bottom and gets deprotonated versus what happens if it comes in from the top and then gets deprotonated. So that's how we form glycosides. And the reverse, why don't you give the reverse a try and see if you can do that on your own. But in the reverse mechanism, we just basically do everything backwards. So you would protonate the OCH3, right? It would fall off, right? Heterolysis. The carbocation would be stabilized by the nearby oxygen, and then water would come in. And then once you have water come in, it would also be deprotonated. And so if you're doing this reaction in a lab, you would control the reaction by the amount of alcohol or water you use. If you add a lot of water, you would force the reaction towards the right. And if you add a lot of alcohol, you'd force the reaction towards the left. Or if you're talking about the top one, alcohol would force the reaction towards the right, water would force the reaction towards the left. Okay, you'll notice that the linkages in the glycosides, the one that we were looking at before, happened at carbon 1. We'll notice that we're numbering from the attachment at the oxygen. So this is carbon 1. If you're looking at this one over here, 1, 2, 3, 4, this is carbon 4. And this is indicating that we have a glycosidic linkage between carbon 1 to the 4 position. So that's what this 1 arrow 4 implies, is the glycosidic linkage between carbon 1 of one pyranose to another. And so we can say that this is a glycosidic linkage. Here's an example of a 1,6 glycosidic linkage. And you can see here again, we're attached to carbon 1 of the first pyranose to carbon 6 of the second. And this little prime, so it's 1,6 prime, and that implies that this is kind of the second group here. It's the same thing that you would get out of the arrow. So you could use 1 arrow 4, or you could say 1,4 prime. Here they're saying 1,6 prime, or you could use 1 arrow 6. Down here we have another 1,4 prime glycosidic linkage, right? The other part that you want to kind of pay attention to here is this alpha versus beta. The alpha part has to do with the relationship or the stereochemistry at this position. Alpha meaning away from the CH2OH group, right? So this is an alpha linkage. Again, another alpha linkage. This one is also alpha because it's away from the CH2OH. Here we have a beta because it is on the same side, on the top face as the CH2OH. So you might want to be familiar with these linkages. This is another beta orientation. The OH is on the same side as the CH2OH. So that concludes this chapter. Here's the study guide for the lecture. Make sure you go through all of these points and you feel comfortable doing all of these points here on the study guide. And please let me know if you have any questions at all.